Yep, it's real. It is unbelievable. Real genius.
Thank you, everybody, for coming to today's colloquium. It's really my pleasure to introduce Ellen McElhatton. She joined my research group in 2013, in the fall. Came out of a chemistry background, and I remember we had a couple of interesting phone calls where Ellen was trying to assess whether she wanted to go do a PhD in chemistry. I think Alaska Fairbanks was like a top runner in that. Or come here and sort of change fields and study atmospheric and oceanic sciences. And so she had a lot of great questions for me, and I remember having a lot of really kind of stimulating conversations on the phone, mostly in response to Ellen's interrogation about what we actually do. But obviously she likes the field, and she's seen it all the way through, and over the last 6 years she's been a very productive member of my group. So she's published a paper, submitted another paper, and has a third paper kind of in the works. I think she's going to be talking today about the second paper. But before I get to that topic, since coming here, Ellen's also participated in a number of field projects. I believe you were down in Antarctica once. She went to Namibia and participated in the Oracle's field campaign we had. And she also...
Marquette, I mean.
Oh, and of course, Marquette in the UP. Shout out to Twitter. And Mark's not here, I don't think, but Mark's work. Yeah, and also welcomed into the world Riley, her son, who turned 2 apparently on Saturday.
Yeah.
So this is going to be a really big week in the history of Ellen. And from year to year to year, you'll be able to tie your PhD defense to Riley's birthday.
Yes.
So anyway, without further ado, I'll hand it off to Ellen here, who's going to talk about, like I said, this most recent paper of hers, which is chronicling the different snowfall regimes over the Greenland ice sheet.
All right, well, thank you, Tristan, for the introduction, and thanks everybody for showing up and supporting me today. I appreciate it. I'll be talking, as Tristan said, about the work we've been doing looking at snowfall regimes over the Greenland ice sheet using satellite observations. So first, for those of you who may not be Arctic specialists and Greenland specialists, I'll tell you a little bit about why perhaps you should care about the Greenland ice sheet in the greater Earth climate system. Well, first, it's important for Earth's albedo. It's unlike the seasonally shifting sea ice, it provides a persistent, bright surface, reflecting incoming solar radiation back to space. And probably most of you are familiar with its role in modulating global sea level rise, global sea levels. There's enough fresh water stored in the Greenland ice sheet to raise the mean global sea level by 7.2 meters. And we know from observations that the Greenland ice sheet has been losing mass beyond natural variability for quite a few decades now, and it's already contributed about 14 millimeters to the global sea level, and it's predicted to contribute up to about 15 centimeters by the end of this century. So snowfall on the GIS, snowfall is what we will be talking about today. And it has 2 main important impacts on the Greenland ice sheet. The first, as you could all probably guess, is snowfall builds the Greenland ice sheet. It's the main positive contribution to the mass of the ice sheet. And second, snowfall brightens the ice sheet. So fresh snow is brighter in the solar wavelengths. It has a higher albedo in the solar wavelength relative to old snow or bare ice. And what that really does is if you have that fresh snowfall on the surface, it can inhibit local melt and retain some of that surface that would have been otherwise lost. But that effect really depends on the seasonal timing. It's only really important during the summer months when you have a lot of that incoming solar energy. So if snowfall is important to the Greenland ice sheet, and the Greenland ice sheet is important to the global climate and predicting where we go in the future, we can ask the question, are we good at modeling current Greenland ice sheet snowfall? And the answer to that question so far is no, probably not. There's evidence that shows that global climate models may produce snow too frequently over the Greenland ice sheet, kind of linked to the dreary Earth problem where global climate models kind of precipitate too often in general. And regional climate models may also be biased low, or may also be biased, and those have been shown to be perhaps low in accumulation over much of the interior. And as I hinted at in the early slides, modeling Greenland snowfall is important. It builds the mass of the Greenland ice sheet, and modeled melt of the surface is really highly sensitive to snowfall representation. Knoll et al. Had a really good paper in 2015 showing that the local reduction in mass and in mass loss from this brightening effect can actually be larger than the increase in mass from the snowfall itself. So really, it's not just how much snow falls, but it's the location, the frequency, and the rate of snowfall are all important pieces for getting the surface mass balance correct over the Greenland ice sheet. So why is it so difficult? Why is it hard to model snowfall over the GIS? Well, there's a lot of factors that influence snowfall. There's microphysical processes within the clouds, there's local surface differences, topography, to the large scale, atmospheric circulation. All of these factors work together to decide essentially where and when snowfall occurs. And it's observations that really drive our understanding of these factors and how they interact with each other. And they also provide model benchmarks. So if a model is predicting a certain amount of snowfall in a given month or a given year, in order to say whether or not it's getting it right, we really have to know that from the observations. How much is it actually snowing? And so far, really no single data set that we have captures the full annual cycle of when, where, and how much it snows over the Greenland, the full Greenland ice sheet. We have a lot of really great data sets that provide insight. Field campaigns can be highly specific in what they're looking for and greatly useful, but they're time limited. It's usually one season, maybe two. Research stations can give really highly detailed long-term data sets, but those are spatially limited. You have that information from one spot, and what's true there may not be true everywhere else. Passive satellites have that coverage, but their sensitivity limited. They can't really, you can't from the passive satellites pick out the snowfall and the cloud characteristics we're looking for over the Greenland ice sheet. And active satellites, which really have revolutionized our ability to look at clouds and precipitation in this region, are wonderful, but they're time limited as well. They've only been up since about 2006. Yeah.
So a quick question.
Sure.
Is the issue that you're identifying with the modeling of the snowfall in Greenland, is it limited to climate models or also to short-term numerical weather prediction models?
Ooh, so I haven't looked at short-term numerical weather prediction models, but I know regional climate models have an issue with it. I know reanalyses also have a dry bias, so I don't know how different numerical weather models are from reanalyses, but basically all the models, from what we can tell from the observations that we have issues representing regionally the snowfall characteristics. So with the data that we do have, though, there are large steps we can make. So really, even if we did have that information, if we knew exactly how much snow falls, we really need to still connect the snow that falls to the large-scale processes and drivers that produce it. And a paper that came out in 2018 by Claire Pedersen et al. Found a really interesting connection between cloud phase over Greenland and precipitation characteristics. And this was using data from a surface station at Summit, in particular it's noted by the star there. And what she found, or what Pedersen et al. Did, was divide the snowfall seen at Summit into two regimes. And the regimes are fairly straightforward. The first is ice clouds, so fully glaciated clouds that produce precipitation, and clouds that contain supercooled liquid water producing precipitation. And what she found, or what they found by categorizing these snowfall into two regimes, that there are distinct cloud processes as well as circulation patterns associated with these two types of events. And what they found at Summit, for what these look like, with the snowing ice phase clouds, you tend to have very deep cloud systems that are, again, fully glaciated. It's responsible for about 35% of accumulation at Summit. And these events are linked very strongly to the North Atlantic storm track. Snowing mixed phase clouds, on the other hand, tend to be very shallow, 1 to 3 kilometers in depth, with a supercooled liquid layer at the top. and are responsible for about 51% of all accumulation at Summit. And these, unlike the ice phase clouds, are linked to quiescent high pressure, anomalously high pressure scenarios over Summit Station. And so what implications do these links to circulation have in terms of the regimes? So first with ice clouds, since, as I said, that Pedersen et al. Linked them to the North Atlantic storm tracks, we've seen in a nice paper by Zappa et al. In 2013 that climate models in general predict changes in both the paths and intensities of the North Atlantic cyclones in response to climate change going into the future. So you can imagine if storm tracks are building the ice sheet with these ice cloud storm events, if you have changes in where these storms are, it's going to change the snowfall that we see. With cloud liquid water cases, on the other hand, and for those of you who are familiar, Arctic mixed phase clouds are another term for these. These are what we're talking about here. This is the quintessential Morrison et al. Diagram of these, and really all you need to know is that they tend to be very shallow, about 2 kilometers in depth, with a cloud liquid layer on top. And these types of clouds are ubiquitous throughout the Arctic. We see them in ship campaigns, flight campaigns, and from space, and they tend to be very long-lived in the Arctic. And the kind of implications that these have in terms of modeling the future of the Greenland ice sheet is they're severely underrepresented and sometimes not included at all in many climate models, both the regional and global. So the goal of the work that I'm going to be showing you today is to expand what Pedersen et al. Showed at Summit Station to the full Greenland ice sheet. And because, as I mentioned earlier, what's true in one place may not be true elsewhere. And so in doing that, we're going to try and answer a few questions. First, how do the two snowfall regimes contribute to the Greenland ice sheet mass and surface brightening, and how does that happen regionally? Are the satellite-derived cloud characteristics consistent with what's expected for the two regimes? And what are the dominant atmospheric patterns that produce Greenland ice sheet snowfall? An outline of what I'll be showing. So first I'll go into the methods. I'll talk about the active satellite sensors that we use, that we leveraged to do this work. Then I'll head into results, where I'll first talk about the snowfall characteristics themselves, then the clouds that produce the snowfall, and then finally link it to that atmospheric circulation, and close with some implications about what we found. So first, how do we expand this study to the full ice sheet? And we do that using two spaceborne sensors. First, Calypso's LiDAR is highly sensitive to cloud liquid layers. It's got a visible wavelength that it can really easily pick out the cloud liquid within the clouds. And CloudSat's cloud profiling radar, which is a 94 gigahertz radar with that longer wavelength, is more sensitive to the larger ice particles and is usually able to penetrate these Arctic clouds to determine whether or not snowfall is likely occurring. And taken together, these two instruments can readily discern coincident cloud phase with snowfall. Oh, and one more note about this for those that aren't familiar with CloudSat. It's got a very small footprint at the surface, about 1.4 by 1.7 kilometers. And since both cloud characteristics and snowfall characteristics vary in time and space quite quickly, giving us this curtain of data, this very high resolution curtain of data, is helpful for this work. So these two satellites were launched in 2006 and joined the NASA A-Train. And what we have here is the 16-day overpass cycle of that satellite constellation. And you can see that the observations are really more concentrated as you reach the top of the overpass of the orbit, which goes up to about 82 degrees north. And so it really provides us with dense observations over our area of interest. And I'll be talking throughout the talk about these observations, and I'll be referring to them kind of in two ways. An overpass is one satellite flyover of the Greenland ice sheet, and a footprint is one of those single CPR measurements. So I'm using all observations for the full data period. So so 2007 to 2016. I will say in 2011, CloudSat experienced a battery malfunction, so it only operates during the daytime. But here in Greenland, that's really kind of more of a seasonal issue. In the summer, when you have 24-hour sunlight, there's no data reduction at all. And even actually in winter, by virtue of the orbital path, it actually operates for a little bit as it moves into polar night, so before it shuts off. And so really we're only lacking about half of wintertime data for the second portion of the observational period. The results that I'll be showing are coming from two data products that are provided by the CloudSat Data Processing Center. The first is 2C Snow Profile, which provides snowfall occurrence and a surface snowfall rate estimate. That is a CPR-only product, so that uses just the CloudSat's radar. 2B Cloud Class LiDAR leverages both the LiDAR and the radar to provide cloud phase, and it also provides us with cloud top and bottom feeds. You'll see here on the right a map of Greenland, and it's divided here into basins. And so these are the Greenland drainage basins that were defined by Zwally et al. It was developed by the Goddard Ice Altimetry Group using ICESat data, and what these are is they're more meaningfully homogeneous than grid boxes, basically, and it lets us look at larger regions of Greenland that have consistent surface slope relative to atmospheric convection and similar drainage areas. So to give you an idea of what these two different regimes look like when we're looking at them from space, here first is an ice cloud, a snowing ice cloud example. On the top here, we have the CloudSat reflectivity swath. So we have latitude across the bottom and we have height here. In the bottom in gray is the surface of Greenland. You can see where this swath is coming from over there on the map. And what you can see here is that this is a deep event, right? This is maybe 7 kilometers in depth. There's a lot of structure within the cloud. And here we have the Calypso backscatter, a little attenuated backscatter. And you can again see kind of the deep event. It attenuates usually within the cloud, though it can penetrate up to a few kilometers. Here we have the 2C Snow Profile algorithm, the data product, and it provides a full vertical column of snowfall estimates. And in the bottom here we have 2B Cloud Class LiDAR, and you can see across the full swath, it's identified this as an ice case. Here we have a cloud liquid water example, or an Arctic mixed phase cloud, and you can see again in the top is CloudSat's reflectivity, now a much narrower system that we're looking at, very geometrically thin. Here we can see the Calypso backscatter, and this line here is now fully attenuating at the top of the cloud. So here at 5 kilometers, you see what would be the top of the cloud system, and the LiDAR isn't able to penetrate at all. And that is really indicative of this liquid layer at the top of the cloud system. And indeed, the 2B Cloud Class LiDAR is identifying this as mixed phase. And what you may have noticed in both of these examples, there's this region here between this structured reflectivity and this surface, there's this bright red band. And what that is known as the CPR line zone. So these are active, this is an active instrument, and so it's sending a signal out and reading or detecting what comes back. And because of the bright surface return, within about 1 kilometer of the surface, ground clutter overwhelms the signal, and we don't actually get any information for those vertical radar bins. And so because of this, the surface rates, and you'll see in both the data products you don't have information in that range, surface rates are based on the CPR reflectivities in the lowest clutter-free bin. So we estimate what snowfall is reaching the surface based on what we see at the top of that line zone. And because of this, you could imagine, since you've got some of these thin systems, perhaps we miss some cases of snowfall. So we wanted to start out by looking and seeing how detectable are these two regimes from space. And in order to do that, we averaged an upward pointing radar at Summit Station to really mimic what the CPR would see from space, and then determine how many of the cases that we know are snowing at the surface would we miss from the satellite observations. And we found that about 22% overall of total snowfall events would be missed by the CPR. And this is a very conservative estimate. We took, even if we averaged in the whole period of time, it only snowed a little bit in what we averaged, we still counted that as snowfall. And, but if you then, what we're interested in are these two regimes. If you look only at IC snowfall events, we actually catch 95% of those. And you can, that kind of makes sense if you think about the swath we just looked at. They tend to be much deeper events with stronger reflectivity in them. So they tend to be caught and flagged as snowfall by the CPR. Cloud liquid water cases, on the other hand, we miss about 25%. We estimate that we would miss about 25% of these snowfall events. And again, making sense because of that much shallower, geometrically shallower events. So I will say that for all of the mixed cases, for the total, for the IC only, and for the cloud liquid water, the missed cases tend to be the very light events. So they have about half of the strength of the cases that we catch. So they tend to be the lighter events. Now we haven't altered the results that I'm going to be showing you in any way based on this information, but I think it's useful to know as you're moving forward kind of the robustness of what we're seeing. So I'll start the results by showing you snowfall frequency. So what we have here is a map of total snowfall frequency in the annual over the Greenland ice sheet. And a few things to note here. There's a north-south gradient. You have more frequent snowfall in the southern half of Greenland than in the north, with a concentration of events down here on the southeast coastline. And this is a very steep incline here along the southeast coast, and so when the storm tracks interact with this part of Greenland, it tends to push the air masses up and you get snowfall in this region. And so this is a very accepted distribution, basically, of snowfall over the Greenland ice sheet. There's a lot of papers that have looked at it, and this is kind of generally what we would expect to see. So we're glad that we see it in our data as well. But what we're trying to add to the conversation is this idea of these two regimes. So here we have the annual snowfall, but now partitioned into snowfall from ice clouds and snowfall from cloud liquid water cases. These two plots add up to 100%. When you have the darker blues, that means there's more. Whites, that means they're less. And so looking at this, you can see that annually, it pops right out that the ice cloud events are more frequent than the cloud liquid water events. And if you take that in the average, about 70% of the frequency is from these icy clouds. There is a bit of an east-west gradient, you'll notice. So there's fewer cloud liquid water cases in the east than there are along the west, which will become a little more important when we're looking at the circulation later on. If we then look just at winter, and I'll toggle back and forth a little so you can see the difference. So this is the annual snowfall frequency. This is winter snowfall. And you can really see now that that gradient is stronger. You can see even less snow is happening in the north, and even more is happening down here along that coastline and off the coast there. And when we break that into ice clouds and Arctic mixed phase clouds, you can see that it's even more stark. Now we have 84% of snowfall is coming from these ice phase events. If we then move on to summer, we see a very different picture in terms of distribution. Now that snowfall is, the frequency of events is really distributed along the full ice sheet. And if we break that out now, what we see is a much more even distribution. You see about 55% now is coming from the ice phase clouds, and 45% is coming from the cloud liquid water cases. And if you remember from the introduction, why we care about this frequency of snowfall really is that it has that effect of brightening the surface, right? So in summertime, when we actually have that peak solar insolation, both the IC and CLW, the ice phase and the mixed phase clouds, really are both very impactful in terms of brightening the Greenland ice sheet. And that's really the take-home message from this first part about snowfall frequency. In summer, when solar insolation is at its peak, ice cloud events and the mixed phase events are both important for brightening the GIS. So before I move on to accumulation, I want to take a minute to look at snowfall frequency that we're seeing from satellite and looking at what was seen at the surface in the Pedersen et al. Paper to make sure that we're really seeing kind of apples to apples. What we have here is regime frequency, which means what percentage is coming from one regime versus the other out of the total snowing cases. So there's kind of a lot going on here, so I'll walk you through this figure because we'll have another one like it coming up. So here we have the seasonal cycle along the x-axis, and icy events, so the ice clouds are in red, the cloud liquid water cases are in blue. The solid lines are the monthly means, and the solid lines are the satellite, and the dashed lines are the surface-based observations. And the satellite observations in this case are only the observations taken within 100 kilometers of Summit Station. So we're trying to compare just what's seen at Summit from space and from the ground. So what you can see first with the cloud liquid water cases is that for both observational data sets, they're pretty infrequent during the winter, and they both peak quite high in July. And that's really, and the ice clouds, on the other hand, are most frequent in winter, and necessarily are the smaller percentage in July and August. And the take home from this is that from different perspectives, different instruments, different years, you kind of get the same answer. Cloud liquid water cases are very important in the central GIS in terms of brightening and adding mass during those important summer months when you're getting a lot of that solar insolation. Cloud liquid water events are roughly double the number of IC in July, continuing to dominate in August. And at Summit Station, Bernard et al. Found that that month actually is the highest month of accumulation at Summit. So really these cloud liquid water cases are playing an important role in this part of the Greenland ice sheet. So moving on from frequency to snowfall rates. What we have here in the top is a histogram of every snowfall measurement taken over the GIS during the entire study period. So that comprises about 2.4 million individual snowfall observations. The histogram has a logarithmic scale, so that means that the vast majority of these cases are light snowfall events. Along the x-axis we have snowfall rate, and that's in liquid water equivalent. So these events here, if you can't see the bottom of the screen, are very light, less than 2 millimeters per hour are the majority of cases. And when you break that out into what fraction in each of these bins is coming from IC in red and coming from cloud liquid water cases in blue, you can see that at all rates, the ice clouds have the larger fraction. The cloud liquid water play the more important role for the lighter cases, but really once you get to about 3 millimeter per hour, all of these cases are coming, the heavier cases are coming from ice-phase clouds. You see the same thing in winter. It's a fairly similar distribution, though now you have an even more stark contrast between the fraction coming from cloud liquid water and the fraction coming from the ice clouds. In summer, you can see that now, as we saw in the maps, you are getting more participation from the cloud liquid water cases, but still, at all the rates, it's really the IC clouds that dominate in terms of frequency we saw in the previous plots. And here, this is really due to low sampling, the up and down. So yeah, it's the bouncing is a product of the satellite, of the product of the sample size there. So the take home from the snowfall rates is that most GIS snowfall is very light, and cloud liquid water snowfall is particularly light. All the high snowfall rates, greater than about 3 millimeters per hour, are uncommon and mostly come from those ice cloud events. And so what this implies, if you take it together, that the IC are more frequent and have higher snowfall rates, you're going to have more of an influence from the icy clouds on accumulation. So moving on to accumulation. Here we now have those Wally et al. Bins that I talked about in the methods section. You can see that our satellite-based estimate of the total annual accumulation of the Greenland ice sheet is about 399 gigatons per year. And if you break that out into the ice-phase clouds and the cloud liquid water, you can see that 318 of those are coming from the ice-phase clouds. So annually, icy events produce 80% of the Greenland ice sheet accumulation. If we look in winter, it's even a larger chunk of it, 88%. And in summer, cloud liquid water plays more of a role, particularly at Summit. You can see the percentage there is a bit darker, and as well in the southern tip in the north, but still, overall, 71% is coming from the ice-phase clouds. So, the take-home from this, icy snowfall plays a dominant role in building the GIS, producing 80% of the total accumulation. And here, it doesn't really matter seasonally, like it did with the frequency. Here, it's just those types of clouds are producing the majority of the accumulation that we're seeing on the Greenland ice sheet as a whole. Which, if you'll remember from what we saw at Pedersen et al., it's different than what was seen at that particular location, right? 51% of what was seen at Summit is coming from the cloud liquid water cases, but when you take the GIS as a whole, the icy clouds are playing a much larger role overall in accumulation. So moving on from the snowfall statistics, we'll have a look at cloud characteristics. Do these clouds look like what we would expect them to based on their regimes? And so what we have here is geometric cloud depth. And again, we have blue is the cloud liquid water, and red are the ice phase clouds. Each of these markers is one individual year's value. So it shows you the interannual variability here, and the blue is just the standard, the shading is the standard deviation between those years. And what you can see here is that it's a very distinct picture between the two. The icy clouds are thicker, they're deeper year-round, about 4 kilometers in depth on average. And the cloud liquid water cases, on the other hand, hover around about 2 kilometers in depth. So this, again, are the averages. So we took all the clouds that we saw in a given month, averaged their characteristics together to get this plot. If we then take a look at the individual cases, look at the distribution of cases, we can get a little better idea of the events that make up that mean. So what you see here along the bottom is cloud geometric depth, now across the bottom, and counts along the vertical axis. These have been normalized, though. Keep that in mind. The relative percentages are up in the corner. There are still far more ice clouds than cloud liquid water cases, but just to get an idea of the shape of the distribution, they've been normalized. So what you can see kind of first off is that the cloud liquid water distribution is relatively narrow and fairly invariant between seasons. There's always a peak right here, right above about 1.5 kilometers in all 3 seasons. So we have annual, winter, and summer. With the ice clouds, on the other hand, the distribution is much broader. You get some cases that are very thin, some cases that are incredibly deep, and that distribution actually shifts between the 2 seasons. You can see the peak here is lower in winter than it is in the summer. If we take a look now at these are 2D histograms of reflectivity. So we composited every snowfall event that we saw over the Greenland ice sheet to create these 2D histograms. We have reflectivity here along the bottom axis and height above ground level here on the y-axis. And what you can see with your, just clearly with your eye, looking at these 2 different distributions, they have different shapes. So with the icy events, you can see that the reflectivity tends to start deeper above ground level than the CLW, and it has this indication of increased reflectivity towards the surface, which can be indicative of growth towards the surface. The cloud liquid water cases, on the other hand, has much more of a rounded distribution, which really doesn't show a discernible growth pattern. And it also, they tend to start, the reflectivity start much lower. If we take a look at what Pedersen et al. Found at the surface compared to our space-based reflectivity histograms, you see a similar idea. So here are the icy snow cases from the surface at Summit. And these are, again, the full GIS. These are all cases, not just the ones at Summit, but the ones over the whole ice sheet. And similarly for cloud liquid water cases. And so what you can see, there's perhaps a more defined relationship that you get just at Summit, but the idea is the same. They tend to be deeper, and you have that indication of growth towards the surface. Whereas for the cloud liquid water cases, you have a distribution that starts maybe closer to the surface and doesn't have that really clean growth pattern or increase in reflectivity towards the surface. So if we take the cloud characteristics together, kind of to summarize, with the clouds containing liquid water, these Arctic mixed phase events, we see that they tend to be very geometrically shallow, up 2 kilometers in depth, seasonally invariant, they show very similar characteristics in winter and summer, and don't have a discernible growth pattern in that reflectivity. The characteristics for ice clouds, on the other hand, tend to be geometrically deeper, seasonally variable, they get deeper in summer versus winter, and growth towards the surface. You see that, you kind of have the idea that the reflectivities are increasing towards the surface. So now that we've had a look at the snowfall characteristics and the cloud characteristics, we'd like to tie what we see in the satellite observations to what's happening in the atmospheric circulation. And to do that, we've taken ERA5 reanalysis product, which provides hourly data, and we've taken from that the 500 millibar geopotential heights and upper level winds. And to define regional snowfall events, we looked at all of the individual overpasses that happened in a given region. We're going to look at a couple different regions. And so in that overpass, it had to contain a minimum of 10 contiguous snowfall footprints, which means you had to have at least 15 kilometers along track where it was snowing. And 90% of the footprints found had to be of the appropriate cloud type. You couldn't have a mixture of the two events. It had to be mostly one or the other. And then for each regime, once we identified all of the cases in a given area, we took the 50% most intense in an effort to try and give us a strong signal to understand kind of what the circulation patterns are that produce these regional events. So, and what we take from that, so I'll be showing you plots of the mean 500 millibar geopotential height, which is just a composite of the nearest hourly value for each of the events. And then I'll show anomalies as well, which are calculated by subtracting the monthly climatological mean from individual events and then compositing those differences. We'll start by looking at the near summit cases. So these are all the cases that we found that came within 100 kilometers of Summit Station. And now this doesn't represent a lot of the snowfall over the total ice sheet. This is less than 1% of the total annual snowfall. But we wanted to take a look at these first to see if we pulled out the same atmospheric patterns that Pedersen et al. Saw at the surface, or saw looking at data from the surface. So first, we'll look at the ice cloud events. So this is the mean of all of the ice cloud events that were near Summit Station, and here are the anomalies. And so what you can see with these ice cloud events is a trough ridge feature here in the 500 millibar geopotential height. You see the trough up above, kind of to the west. Greenland is here. I've highlighted Summit with a little star. And you can see that the winds, hopefully you can see, that the winds are coming from this kind of the south-southeast into Summit Station. In the anomalies here, you can see a dipole. You can see higher than average heights here off of Iceland and lower than average heights here off of the northwest corner of Greenland, and with strong anomalous winds that are in kind of the same direction as the new winds. And what this pattern does is it really resembles synoptic conditions that are often talked about and credited with producing Greenland ice sheet snowfall, and through their association with kind of the storm track activity here. So it's been identified, Chen et al., Rogers et al., Zares and Bear, they have all talked about kind of this pattern producing Greenland snowfall. If we look at the cloud liquid water cases, on the other hand, we see quite a different picture. So now we have much more uniform mean heights indicating kind of calm conditions over the ice sheet with slower mean winds around summit. And what you see here down in the anomaly is quite a different picture than the other. You see this very higher than average heights over the entirety of the Greenland ice sheet. And previously, persistent high pressure anomalies like this one have been connected with GIS precipitation, both in Hanna et al. As well as the Pedersen et al. 2018 paper. So overall, you can see there's markedly different circulation patterns for, again, the ice phase clouds and the Arctic mixed phase clouds that are producing precipitation. And these are, again, the cases that only came within about 100 kilometers of summit. And so these are very similar in character and magnitude to what Pedersen et al. Showed in their paper. But the strength of this work in the satellite approach is that now we can look beyond summit and see what conditions bring snowfall to regions without these intensive ground-based observatories. So first, we'll have a look at the northern Greenland cases. So these are the cases that came within these 4 drainage basins here at the top. This isn't a huge contributor to total annual snowfall, as you saw in the early slides about frequency. This is not a place where it snows all that often, but it's interesting because we don't have a lot of observations in this area, so it's curious what does actually bring snowfall to the northern GIS. So here, again, we have the 500 millibar height mean and anomalies. And now you still do have a trough to the west of the GIS, so now it's a bit oriented differently. You have kind of calmer upper level winds. And again, you see a dipole in these anomalies. But this time oriented quite differently than they were in the previous plot. So now you have this lower than average heights here off the eastern coastline and higher than average heights off the kind of southwest tip, kind of directing this anomalous flow. You can see the circulation here, and the anomalous flow is now coming from the north part of Greenland into that northern area. The cloud liquid water events, on the other hand, again, now we see these uniform mean heights, calm conditions, and higher than average heights over the whole GIS. As opposed to the summit cases we were looking at, the higher than average heights is centered over Baffin Bay now, but you still see that overall the whole Greenland is under these higher than average, these anomalously high geopotential heights. So the common themes through this: trough to the west, dipole in the anomalies for the ice clouds. For the cloud liquid water cases, relatively uniform heights, kind of a strong anomalous ridge. And so that's for the northern cases. Now moving into the western GIS cases, so you have that large red highlighted area. This is now a bigger chunk of the snowfall that's received by the Greenland ice sheet, 39% of the annual snowfall. And you can see here for the west, again, you have a trough, again, oriented a little bit differently than the previous ones. And in the anomaly, you have still a dipole. The lower than average heights are a little bit less distinct than the previous, but again, now the dipole is located in such a way that these anomalous, the anomalous flow is into our region of interest. And the cloud liquid water cases, more uniform heights, again, a strong anomalous ridge, but again, centered in a different spot such that now the anomalous flow is into our region of interest. And finally, to the southeastern GIS, so now highlighted in those red regions over there, 36% of the annual precipitation, so this is another big contributor to the overall snowfall accumulation on the ice sheet. You can see now a much more pronounced trough here to the west of Greenland, kind of extending down to the bottom, and quite a distinct dipole here, and now the anomalous flow is such that it's coming right into that area of interest off of the North Atlantic. In the cloud liquid water cases, I would argue that this is not as uniform as our other regions. You have a little bit of an indication of a trough, but much more uniform relative to the ice cloud pieces. And you have, again, an anomalous ridge over the ice sheet. So taking these all together, there's common themes for all of the regions. With the ice clouds, there tends to be a trough to the west and a dipole over the Greenland ice sheet in the anomalies that tends to direct the anomalous flow into the region of interest. Cloud liquid water cases, on the other hand, tend to have relatively uniform heights, but an anomalous ridging over all of the ice sheet. And so these results point again to the ice cloud snowfall being consistently associated more with cyclone-type activity and North Atlantic storm track type activity, while the cloud liquid water snowfall in all the various regions tends to occur under quieter, high-pressure scenarios that I didn't mention earlier, but that is the kind of scenario that tends to favor these long-lived Arctic mixed-phase clouds. So to summarize, to kind of bring it all together, for the ice cloud snowfall observations, we've seen that IC is responsible for 80%, so the majority of building the ice sheet is coming from these ice phase clouds. The CPR has high skill in detecting these events. It probably captures about 95% of them. They tend to be geometrically thick, about 4 kilometers in depth, and associated with cyclone activity. Whereas the cloud liquid water, on the other hand, while it's not responsible for most of the accumulation, it's responsible for about half of that brightening effect in summer when solar insolation is at its highest. So these clouds really, this snowfall regime really plays an important role in terms of the surface mass balance of the ice sheet. Not in total accumulation, but in that brightening effect. The CPR has a slightly harder time detecting these, but still catches about 75% of them. They tend to be geometrically thin and associated with that anomalously high 500 millibar geopotential height and bridging over Greenland. So some of the implications, kind of coming back to what we talked about a little bit in the introduction of these results. So our work, it's only about 10 years, so it really provides a snapshot of snowfall characteristics within a rapidly changing Arctic climate. But that snapshot is useful in that it allows us to connect the snowfall that we see to the larger scale atmospheric drivers. And when we see with the ice clouds being associated with those North Atlantic storm tracks, we know from the Zap et al. Paper that North Atlantic storm tracks are predicted to change in the warming climate. And so some future work that we're thinking about doing is mapping our regime-based results onto the predicted changes that will occur in these storm tracks, which may hopefully yield additional insights into how the GIS might respond to the warming climate. With the mixed phase clouds, on the other hand, we saw that maybe they're not as important for accumulation, but they are very important for that surface brightening effect. But we know that climate models are notorious for underrepresenting or not including Arctic mixed phase clouds at all over Greenland. And so if those clouds aren't represented, the snowfall can't be either. So some future work that we're talking about doing moving ahead. So the Community Earth System model, which is one global climate model that's fairly popular, has recently released a brand new model version. It's gone from CESM1 to CESM2. And part of that model change is they really wanted to address some of the long-standing cloud biases that they had in this model. So this is just an example from a previous paper we did in Journal of Climate in 2017. And these are mixed phase clouds over Summit Station. And so in the blue are satellite observations, black are surface-based observations, basically the same over Summit Station. And these are not snowing or not snowing, these are all the liquid containing clouds. There are quite a few in summer, particularly over Summit. But in the old version of the model, the red here at the bottom, there was virtually none, right? They just were not represented at all in that model. So we know in CESM2, they made great efforts, and it's been shown that they've improved the northern hemisphere circulation in general, and they've also increased 6-fold the amount of Arctic supercooled liquid that's in the model. And in another paper that we should be submitting at the end of this month, we've shown that in CESM1 model versus CESM2, Again, the majority of the changes are within the microphysics of the atmosphere. We see a huge difference in the water equivalent snow depth on the Greenland ice sheet. And these are the mean state of the model, basically. And we have a huge change in the mean state of the Greenland ice sheet in particular. And it's a change in the snowpack over the GIS of greater than 9 meters, and that's snowfall water equivalent. That's not 9 meters of snow, that's 100 meters of snow, depending on how you calculate the density of the snow, but that's not a small change in the mean state of this model. And so we'd like to really take our regime-based approach and put it onto the changes between these models to see whether or not it's really increased due to a change in the cloud liquid water cases that now exist that are perhaps providing snow, or changes in the way that the circulation is represented within this region. So with that, thank you all for listening. I want to acknowledge NASA for providing funding. I was lucky enough to receive the NASA Earth and Space Science Fellowship for the last 3 years. I want to thank Tristan for bringing me out here. I made a good bet, I think, on coming to Madison, and thanks to my committee for your guidance. I'm a better scientist for it, and I really appreciate all the time and patience you've had with me. Thanks to the greater AOS faculty and staff for support along the way. I've really felt like a member of this community, not like a number, so I appreciate you all for making the effort to make it feel like an inclusive environment. Big shout out to Pete for saving me many times with computer disasters. You are a gem, and this department is very lucky to have you. Thank you to the Lequier Research Group for the past 6 years. It's been a delight. We started a little smaller than we are now, but it's really been fun seeing where everybody's science has gone, and it's been a really supportive group, and I appreciate that. And outside of my own little group, I've made so many friends within the AOS community. As Tristan talked about, I got to go to Antarctica with the AMRC, my science breakfast, my polar coffee folks. It's really been, it's been fun. It's been a fun 6 years. And I couldn't have done it without the support of both the Lequier group, the greater AOS community, and my wonderful family. As Tristan mentioned, my son is now 2, turned 2 on Saturday, and without the wonderful support of my mom, who is somewhere in this building with my son right now, taking care of him, my family really made an effort over the last 2 years to help me both finish my PhD and raise this little feather. And Wisconsin in general. Thanks, Wisconsin. I had not been here before I came out for this program, and it's really just been such a fun place to get to know and to be for the last little bit. So with that, I will take any questions that you have, and thank you for your attention.
So I have 2 questions. My first one for your circulation composites.
Mm-hmm.
Whenever you say you have, say, 400 cases,
Okay.
Do you mean you have 400 days? You have 400 independent events? I guess how many independent events do you actually have for those composites?
So let's pick one. Okay, Western. So so we started with total flyovers. So each one of those occurs only once, maximum every hour and a half, right? And we took all of them. So for the ice clouds, we would have had nearly 2,000 cases for this, and then we took the half that were strongest. So there could be some that have, it is possible that we flew over the storm more than once, and that could have impacted our results.
My other question?
Yeah.
So whenever you were looking at your histograms of the reflectivity in the cloud depth, and you were comparing it to the results of Summit?
Yes.
Yes, this one?
Yes.
If you were to take your results using satellite data
Mhm.
and looked only over Summit,
Mhm.
would they match?
Yes, so we've done that as well. So those looked quite similar, and what I wanted to do here was really kind of expand and show that we do see similar characteristics over the whole Greenland ice sheet. Because there's some characteristics that are the same between, you know, satellite at Summit and ground-based at Summit, but this one actually you see just ground-based at Summit does look like the whole GIS. Yeah.
While we're looking at this one, is this also limited to just cases that are producing snow at the surface? Or
Yes.
these all
Yes, these are only snowfall producing cases.
We did some studies years ago on these mixed phase clouds with Hildner and Rogers group and all this, and observing them up in the region. And one thing we
Yes.
found is that they're highly dependent on aerosol sources, that these clouds usually are associated with trajectories that are coming off of industrial areas like Asia, Northern Siberia, and Europe. Have you looked at all of that? Does that seem to match what you're thinking?
Not specifically, we haven't looked in that, but I could. No, I have not looked at that, and I'm not gonna extrapolate the thought that I'm having. But I think that that's worth having a chat about and looking into in the future, like doing a further back analysis on where these air masses are coming from beyond, you know, just the ridging when they appear, whether or not those air masses are coming maybe from regions of these high aerosol areas.
We've done quite a bit of study on why they're mixed phase. And we know they're mixed phase because of the effects of the aerosols acidifying the liquid solution so that it can't freeze. And when the droplets grow and become big enough, they are dilute enough that they actually can reach freezing. And so they have ice showers coming out of them while they maintain the liquid base. And it's because of these acidification from the aerosols that are occurring in the cloud condensation nuclei.
I'll have to take a look at those papers. So I'm mostly familiar with kind of the Morrison et al. Perspective and diagram on these papers, and it's a lot of, they point to a lot of different factors coming in together, but that isn't one that I've thought of highlighted before, so
There are a number of papers on this.
Yeah.
Can you go back to your mean figures that showed the any one of like the ones that are there?
Sure.
Just this is a minor thing. I don't think it doesn't at all change the conclusions, but I think the way the winds are plotted, or you may have to rotate the vectors.
Nope, that comes from Claire.
Because they seem very aetiostrophic at 500.
Stream. Those are straight from Reno.
No, but there might be, is it in the map? Is it in
Yeah,
the, it's in the,
What is it called?
Yeah, it's in the correct.
Quick framework.
Coordinates.
They are really aetiostrophic.
They're extremely.
Yeah.
Again, I don't think it changes the overall result, but just something.
I mean, it could.
Are there any trees fall for working time?
Yes, yes. Mostly along the coast. The question was, is there rainfall over Greenland? There is rainfall over Greenland, mostly at the coast, and it does contribute to the mass of Greenland. So if it rains into the firn, when you have that lightly packed snow, that can actually add to the mass of Greenland. None of these data that I'm looking at here include rainfall. These are all snowfall only precipitation events.
Except I'd like to tell the crowd, because your thesis is so well put together and so well written, you do mention in your chapter 4 that the CCM version 2 is raining too much
Yes.
in freezing temperatures.
Yes.
So there's something wrong with what's going on in the new version of Model 2.
There is.
It's worth
So that's,
saying something about it.
modeling is a hard world. I wouldn't call myself a modeler, but I have great respect for the modeling community and their efforts in trying to constrain the whole world all at once and all of the problems therein. But yes, in the new version of CESM that I alluded to, that has the very different representation of the snowpack over Greenland, there's so much liquid water in the clouds now that it is literally sedimenting out of the bottom of the clouds. And there's not a specific freezing mechanism for it, so it's rain. And it's raining in January, it's raining all year, unfortunately, now in the Arctic in the new model. So there are some problems that have been added, along with some of the fixes that they've been trying to make. Yeah?
You mentioned the added albedo from the precipitation from liquid clouds.
Mm-hmm.
I wonder though, the liquid clouds also produce added albedo just by their presence.
Yes.
And what's the relative magnitude of those two effects?
So, I don't know is the answer of the relative added effects, but since you bring that up, I will point out something that was not a focus of this work, but I've touched on it in other places. So these mixed phase clouds produce precipitation, but also by virtue of their phase, they are great insulators, right? So they may be adding snowfall that's increasing the brightness of the surface, but they have this competing effect of these clouds are also, when they're not snowing, Arctic mixed phase clouds are credited with a lot of the melt events that happen over Greenland. So they have, there's a lot going on, essentially, with these mixed phase clouds outside the scope of this 1 hour talk. But yes, thank you for putting that out.
All right, speaking of 1 hour talks, I think this is probably a good time to wrap up because we're right at the hour. So let's thank Ellen again for a great presentation. And the members of her committee, Ellen, do we have a room? Where are we?
Oh, I thought we were
just going to meet here? Okay, so we'll just reconvene here in about 5 minutes.
I didn't know that was my bad.
No, that's fine.